Welcome to Lesson 15C, Cumulative Distribution Function. We're going to use the same example sample that we did in the previous lesson. I have it recopied here, skipped a few columns in between where we had all that histogram stuff and probability stuff. The most important columns are the ones that I have shown: the class or bin number J, the minimum and the maximum particle diameter in each bin, the middle diameter in each bin. And then we worked our way through and got the probability in each class or bin, which was given by this definition, but it's also equal to Nj over Nt. And I'm not listing Nj here. We're interested in the cumulative distribution function, which you may remember from statistics class. Cumulative means we're adding things up. In this case, we're adding up probabilities. What this capital F of dp means is the probability that a particle is in this class or any of the ones below it. So for the first one, it's the same as the actual probability of that class, 0.104 or 10.4%. For the second bin or class, j equal 2, we calculate it by taking this value and adding it to the probability of the second class. And when I add 0.104 and 0.16, I get 0.264 or 26.4%. And you could keep doing that. 0.264 plus 0.161, which gives you 0.425. This is where Excel really comes in handy. Once you have this set up, you can just fill that down for all your bins. What does this mean physically, this 26.4%? It means there's a 26.4% probability. It includes both bin 1 and bin 2 in their entirety. So 10.4% is the probability that a particle lies in bin 1, which is all particles less than 4 microns. 16% is the probability that particle lies in the second bin, which includes all particles between 4 and 6 microns. In other words, all particles below 6 microns, but greater than 4 microns. And when we do a cumulative distribution, we're just taking both of those. Therefore, it's probability that a particle is less than or equal to 6 microns. This is an important comment. We plot the cumulative distribution function against maximum diameter in the class, not minimum or middle diameter. So even though I have this dpj middle value highlighted, I put a box around dp max j. We plot f of j as a function of dp max j when we want to plot cumulative distribution function. Note also that if we add all these up in this column, we get 1 or 100%. But in the capital F column, the one on the far right, this asymptotes to 1 or 100%. And that makes sense because what we're saying is that the probability of a particle being less than 100 microns in this case is 100%. In this particular case, there were no particles in this last bin, so we could actually say that there's 100% probability that a particle will be less than or equal to 50 microns. Be careful here. This is one of the biggest mistakes that I've seen in student work when I have taught this course before. Let's plot capital F of dp, this last column here, versus dp max j, the upper limit of each bin, the third column from the left. And I called that plot 6, the cumulative distribution function. We don't go all the way to 0, so we don't have anything in here. But notice that this asymptotes to 1 or 100%. Just as a quick sanity check, this 26.4% for bin 2, which has a dp max of 6, this is 6, and this is our 0.264 or 26.4%. So that agrees with our table. I made this plot simply from that table. Why do we plot cumulative distribution function against dp max j instead of dpj? Well, let's go back to our plot 3 of the previous lesson, which I just copied again here. This was our histogram of fraction per class width. This was the one where I modified the y-axis here so that it's independent of total number of particles, Nt. If you recall from the previous lesson, the area in one of these histogram bars is a probability that dp lies in this particular bin. The first bin goes from 1 to 4 microns. The second bin goes from 4 to 6 microns. This is bin 1 and bin 2. So this blue area is the probability that dp lies between 4 and 6 microns. And that 6 is dp max for that bin. When you add up these two areas, you get the probability that dp is less than or equal to 6. Includes both j equal 1 and j equal 2 bin areas. And if you look at our table, this area for bin 2 was 0.160 or 16.0%, and this red area was 0.104 or 10.4%. When we add those two areas together, we get 0.264 or 26.4%, which if I scroll back to my table is the value that we had up here for bin 2. So you see that you have to include the DP max. You're including the entire bin when you do this. So that's why we plot against DP max, not DP middle. We can also say that this is the probability that DP is less than or equal to 6 microns. And we can go all the way down to 0, even though we don't have data down there, because we're doing this for our particular sample. And for our sample, 26.4% of the particles are indeed less than 6 microns. Let's talk about the cumulative distribution function from statistics that you would hopefully recall. We'd usually use X instead of DP, but we would plot f of DP, the PDF, as a function of DP. And for particles, we typically have this log normal type of function. If we define some dp that's equal to a and go up to the curve, this area is equal to the cumulative distribution function, capital F of dp, at dp equals the value of a. So we call this f of a. Mathematically, f of a is just the integral under the curve from 0 to a, and it's the probability that dp is less than or equal to a. A little side note here, our A is our dp max j, not the middle value when we're doing this with discrete values instead of a curve. Some comments about this curve. First of all, f of infinity equal 1. The area under the whole curve has to equal 1 or 100%. In other words, if we take our A way out here at infinity, we get the entire area under the curve. And remember, the entire area under any PDF has to be 1. What if we have another value B? Then f of b minus f of a will be the green area, because it's the area below b, everything less than b, minus the red area, everything less than a, and that gives you the green area that I sketched. Mathematically, it's the integral under the curve from 0 to b minus the integral under the curve from 0 to a, which can be reduced to integral a to b of f of dp ddp. You may remember tables for f of a that you use in statistics class for Gaussian distributions and student t distribution and other distributions that we talked about. It's the same idea here, except these are typically log normal distributions. There's a special case at some value of dp where f of that particular dp is 0.5 or 50%. We call that dp50, or the median diameter. Remember from statistics class, median is not the same as average. Median means 50% of the values are bigger than it and 50% are smaller than it. So capital F of dp50 is 0.5 at dp equal dp50, and I'm going to put in parentheses number because this is a number distribution. We can also do the same thing for mass if you have a mass distribution instead of a number distribution. And since bigger particles weigh a lot more than small particles because of the cube of dp, dp50 mass is not the same as dp50 number. You can repeat all the algebra we did for mass distributions instead of number distributions to calculate this. For our example sample, we get dp50 equal 9 microns. I can go back to my plot and see this special case at 0.5 turns out to be 9 microns. Or better, looking at the table, it turns out that we have exactly 0.5 at dp max is 9 microns. Now here's a warning. I've taught this course many times, and if I give a problem on the final or on a quiz where I give you a table like this and then ask what is dp50, a lot of students will choose 8.5, which is the middle diameter, but that's not correct. It's the maximum diameter for that bin. What it means is half of the particles are smaller than 9 microns and half of them are bigger than 9 microns. Now, one final comment about these distributions. For a normal distribution or a Gaussian and normal mean the same thing. If we had a normal distribution of particles and I plot the PDF, it would be symmetric and be a Gaussian, and dp50 would be right at the middle at the peak. That's because it's symmetric. All it means is that this area is 50% and this area is 50%, and it's divided perfectly equally down the middle. But for a log normal distribution, which as I said before is more typical of air pollution problems, our PDF looks more like that with a very long tail. It's not symmetric. It's not normal. Hey dude, since it's not normal, can we call it abnormal? Well, Joe, I suppose that anything that's not normal is abnormal. turns out that DP50 is not at the peak. In fact, it's to the right of the peak. Again, these two areas have to be the same, 50% on the left and 50% on the right. The reason this DP50 does not occur right at the peak here is because of this long tail in order to balance 50% on each side of DP50. That's how it turns out. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.